Hi, in this video, we want to take a look at extending principal component analysis to three-way principal component analysis. So think about a regular data set. A regular data set is going to be in a matrix or data frame, and that's going to be, a two-dimensional table of data, right? And then, we go through and we take our geometry off of that two-dimensional table of data, and we get our principal components. All right. Well, what is a three-way principal component then? Well, in this case, we're interested in where, I have rows, columns. So rows, columns, just like in a regular data set, but I also have like layers. So I would be representing my data as like a three-dimensional coordinate system. So I have rows data, I have rows, columns, and like layers of data to work with. So it's going to be a three-dimensional array is how we're going to store our data. And from this, we want to get, something similar to principal component analysis. Now, something about this is that because we're going into a higher dimension in terms of like geometry of it, it becomes ambiguous as to what extending PCA is. And so is PCA like representing the entire data set, like it does with component one, component two, or is this approximating like the first dimension and the second, the or maybe the second and the third, the first and the third, something like that. So here, when we talk about extending principal components, we have to be more precise about what we're talking about. So we're going to go over two different ways. The first one kind of works on getting like an overall representation of the entire data set. That's like one feature of PCA. Other one is like dimension wise is trying to do an approximation specific to the dimensions that we're concerned about at the particular time. Both of them are extensions of principal component analysis, but the geometry of higher dimensions is a lot more complicated. And if we go up to 4 dimensions, it becomes even more interesting. All right, so this example is modified from Modern Psychometrics with R by Mayer. Here's the GitHub page for the code that I used to I modified for this video. All right, so here we have three-dimensional data. We have 3 in particular. So we have a subject, an individual, an item, and then a year. All right, so the same person gets asked the same question over multiple years. Okay, and then all the subjects get the same questions and over the same years. So there are 2 major ways to be doing this 3-way principal component analysis. The parallel model, what this does, this finds components that are common to all dimensions. The Tucker 3-dimension method, what this does is each dimension gets a component. And so if I'm interested in subject, then I would be taking the subject principal components. If I'm interested in items, I would take the item principal components. If I'm interested in years, I would take the years principal components. And so that's how that will work out. So parallel, because there's only there's kind of like universal components, it's going to be the easier one to interpret, easier one to figure out. The Tucker 3 one will be more nuanced and will actually give us more information, but you're going to have to be wading through some stuff to get some good stuff out of it. All right, so let's go ahead and get some data. So what we're going to do from the MPsychoR package, which goes along with the textbook, we're going to load our data. We're going to look at longitudinal social dominance orientation, SDO. And so there are 4 items measured across 5 years, and each item is scaled from 1 to 7. And here are the questions. It's probably a good thing that certain groups are at the top and other groups are at the bottom. Inferior groups should stay in their place. And then here, the next 2 were reversed. So if the person said 7, it gets converted over to a 1. If the person said 1, got converted to a 7. And that's to get parallel scaling on all our items. We should do what we can to equalize conditions in different groups. And then increased social equality is beneficial to society. And so you can see that 1 and 2 kind of like are along like a similar scale. If you say strongly agree, strongly disagree, 1 and 2 are going to be more similar, while 3 and 4 are going to be like opposite directions on that. All right, so here I am suppressing some output just so that we don't get blasted in the face as we read through this. Here I'm loading the data. Now, all the data was on a 7-point scale. So what I did, I went, well, 4 is in the middle of 1 to 7. So I subtracted 4 from everything. So I'm taking the mid-range and I'm subtracting off. And I do that, this is similar to subtracting off the mean of each column, but since I have a constant scale, I just went with 4. That way 0 I know is like the middle, and then plus or minus 3 are the extremes. Now on the next one, I use the array function to convert over the data, which is into an array format. I need to do this to be able to run the 3-dimensional principal component analysis. So as it comes to me, it's with rows and columns. And so a subject is a row, and then a column is a year and an item. I want to break this up. And basically I'm copying this from the author of the textbook. Here is the data. I'm unlisting it so that it becomes one long vector. And then I pass it to the array command to go through and put it in the right format. Now, the author had definitely spent some time looking at how the data is arranged and how the unlist function operated on this before doing that. And now here I go through and I just go ahead, I put down the dimension names on there. So here is subject's IDs are 1, 2, 2, 12, or 6, 12. Here's the items for 1, 2, 3, 4, and then the year. And by doing this, this step isn't necessary, but it makes it easier to remember, easier to identify what I'm doing. All right, so now the parallel factor model, which is parafac function, what this does, this is going to find like universal components across all dimensions. And so there's going to be, so realize that I've got, in my dimensions, I've got subject, I've got item, and I've got year. Okay, so when it goes through and does, it's going to find some matrices as part of the process. The first one goes with the first dimension, and that's going to correspond to subject. And this is going to be dimensions I by P. I is going to be 2 or 6, 1, 2. B is going to correspond to the items. We can also think of it as the loadings matrix. And this is going to be J by P, which is J will be 4. And then year is our last one. This is going to correspond to C, and we're going to call that the occasion because it corresponds to the year. And K by P, here, K is going to be 5 because we have 5 different years. All right, and so now P is going to be the number of components we choose. I choose 2 every single time in these examples because I can plot 2 on a scatter plot. I would actually start like digging in if this was a real project, but for the purpose of the example for the video, I kept it down to 2. Usually 2 does a pretty good job in a lot of situations. Now the actual model itself is that the modeled value of the individual's response on, so subject I, question J, year K is going to be this formula here. So you'll notice I have AI, so remember A corresponds to the subject, BJ corresponds to the item, and CK corresponds to the year, and then the P is for either the first or second principal component, which I define. All right, so here the coefficients that we have coming off these matrices is that these can be interpreted as a relative importance of the component for the ith individual, jth variable, kth occasion. So my A, B's, and C's are the relative importance for that individual item year combination. And so because all of them are being in one pot for all dimensions, parafac finds components that are common to all 3 modes. Now, something about this is that parallel factor models are unique and they cannot be rotated without degrading the fit. So based off the data, we're getting the best fit possible for this model structure. Now, if I get the best model possible, because of the linear algebra dimensions of this, I can't do any rotations at all like I could with the with factor analysis. And parallel factor models are not orthogonal. Now they could be by happenstance. Just assume that they're not. They're probably not. And so something that's nice about this compared to the other model that we'll look at, because there's less going on, there's fewer things there. This is easier to interpret because I have less things to look at, less things to wade through. So implement this, we're going to use the multi-way package. And the other example will also be with the multi-way package. We're going to use the parafact function. I say the data I want and the number of factors. And something I also want to do, I want to set C to make sure that this is reproducible. And so then we get some output. So this is just indicating how far along the process it is. And then I can get the output. So here, I can see that here's my standard squared error. So, when you were talking about this, remember I have X, I, J, and K. So, we can have a good number of individual items to be, take the difference, square it, then add it up. Here is my R squared. Now, I actually modified this. I explored several different models before this video, and this is a better R squared than what the textbook had. The textbook had basically a multi-dimensional center and scaling, and I played around with different centers and scalings, and I found that none was actually the highest R squared. So this is the version I'm going with. If you look through modern psychrometrics with R, he subtracted off the mean but for each response, he subtracts off the mean for that item that year. And we always want to check to see if it converged. If it did not converge, we don't trust the results. And remember, if it takes a lot of iterations for something to converge, it's probably a poor model structure for your data. All right, so now on this step, what I'm doing is I'm going through and I'm tacking on names onto my output. So here I've got the output from the parafact function, and I have my A, B, and C going on. Well, I go ahead and I slap on the dimension names from the array just so it's easier for me to spot. So here, this is kind of like my principal components if I'm interested in subjects, right here. Then here, this is my principal components if I'm interested in item, and here are my principal components if I'm interested in year. So here's A, here's B, and then down here is C. Now, I know that I'm getting principal components for all three of them, but they're all computed off of the same model. And so this is different than the one that we're going to look at in a moment. There'll be, the calculations will be much more separate for the upcoming model. All right, so now let's go ahead and let's do some plotting. Let's look at a biplot. So here, each subject is a gray dot, and then the items are on the biplot arrows. And so here we can see that where the items are pointing. So we can see that 1 and 2 are very close to each other. 3 and 4 are very close to each other. The first dimension is kind of like, you see that all 4 are pointed in the same direction. That's after rescaling. So that's kind of like an overall response. The second dimension is really detecting the difference between 1 and 2, like together, with 3 and 4 together. So my interpretation is that the first component tells me about where is an individual on a spectrum overall, and then the second component kind of breaks up those 2 questions, breaks up those 4 questions into 2 groups. and see, it's kind of like, I'm an English person, I'm a math person. You hear people say that. That second component is like, where are they on the math scale, English scale aspect? All right, next, let's go ahead and look at things by the year. And we can see that things are really stable across the different years, that we don't see a whole lot of change across time. So it gives me kind of like a good overall summary of what's going on. And so now let's go ahead and get our sum of squares error. This is more like mean squared error, by the way. So it's 0.88. All right, so now let's do another model for three-dimensional principal component analysis. This is going to be the Tucker 3 model. So what this does, each mode gets its own specification regarding the number of components to be extracted. So here we're being more specific. All right, like I want potentially 5 principal components for subjects. I want 2 for items. I want 3 for years. I have the flexibility. And because of this flexibility, these principal components are more like separated out, and they're going to be, this is going to be a more complicated model to interpret. So when I go through, P is going to be the number of dimensions for subjects, Q is number of dimensions for items, R is number of components for events. So now the number of components need to follow some inequalities for the linear algebra aspect to make sense. For the computer to be able to compute it, we need to make sure that each individual number of components is less than the product of the other two. So P has to be less than or equal to Q times R, and Q has to be less than or equal to P times R, and R needs to be less than or equal to P times Q. Now, the default algorithm for Tucker produces orthogonal components. Now, these can be rotated if I desire. Okay, so our interpretation of A is this kind of like, this is going to be considered like prototype subjects. So this is going to be like modeled subjects based off the data. Then B is going to be our loadings based off the items. C is going to correspond to the year. And so this is like the trajectories or latent curves. So this will be like a latent variable for the population as a whole. Now G is going to be a matrix that's P times Q times R. This is like the core array. We can interpret this as the weight or strength between the components across all modes. So this is going to function similar to singular value decomposition, singular values, but it's like the 3-dimensional version. So it's a more complicated singular value presentation. And our formula is going to be the modeled value for each subject. For subject, question, year is going to be this summation or across the dimensions, where I have A, B, and C like before, but I have G also being multiplied on there. And then I have, summation across the dimensions. So there's a lot more flexibility in this one. And also this extra parameter enables more fitting. Now, if I am going to make it pretty tight between these inequalities, and I make a lot of components compared to the number of the amount of data I have in terms of columns, rows, and layers, then I can definitely overfit on this one. This is one that's going to be more prone to overfitting than the parallel factor model. Tucker models are not unique, and we can rotate them without degrading the fit. So if I want to have some flexibility so I can try and find one that a rotation that is easier to interpret, I can go ahead and do that. With a parallel factor model, I can't do that without making the fit worse. And by default, the components are automatically orthogonal. And so now, once again, in the multi-way package, I use Tucker. I put in the data and I put in the number of factors I want. And here I'm just doing 2, 2, and 2 because that's easy for a scatter plot. Potentially, I could have any 3 numbers as long as those 3 inequalities are respected. And then, we go through and we just tack on some dimension names to make it a little bit easier. And the output is very similar to the parallel factor model. We get our sum of squares error. We get our R squared. Once again, I did not center and scale this data because it gave me a better R squared. And it converged in 6 iterations. And I'm slapping on dimension names so that when I start looking at the output, it's easier for me to remember if I'm talking about subjects, items, or year. All right, so the A matrix, this is my principal components for subjects. This is my principal components for the questions. This is my principal components for the years. And now G is going to, remember I went 2 by 2 by 2. So I'm going to have a 2 by 2 by 2 array for G, and these are the values. And we can go through and like here, we see that this is a very big one. So G, this one for, see that's 1, 1, 1. That's a very large value. So I see that that has a lot of weight. That's a very important one. Then the next biggest one is going to be 2, 2, 1. And then after that, it's going to be 2, 2, 2. Now let's go ahead and do some plotting. Let's do the biplot. And really, this looks pretty similar to what's going on. If I look horizontally, the item arrows are all pointing in the same direction. So remember that 3 and 4 were reversed in their scaling. So I can see that like their overall response is their first principal component for A. And then the second principal component is like the distinguishing between 1 and 2 together, 3 and 4 together. And then let's take a look at the occasion curves. So we can see that component 1 stayed very flat across the years, but component 2 changed wildly. This is interesting. So I would definitely want to see what was going on in 1997, what was going on in 2000 that's different than the other years. Why did this dip down and go back up? All right, well, that's all I've got for you. Take care and goodbye.